Hello, grade 11s, and welcome to our first lesson on the gas laws. In today's lesson, we're going to be doing conversions between the various units for temperature and the various units we can use to measure pressure. In the gas law, all of our formulas are very unit specific, and there's lots of ways we can measure these things. So we have to learn first how to do conversions between temperatures of different types and between pressures of different types. Now, when we measure temperature most often in our lab or in our houses when we're cooking, we tend to measure in Celsius. Now, Celsius is a temperature system that's based on water. We know water freezes at 0 degrees, it boils at 100 degrees, we divide that up into 100 equal sections. That's our Celsius temperature scale. In America, they don't use the Celsius temperature scale. In fact, even on our ovens, we won't necessarily use the Celsius temperature scale. They would use the Fahrenheit temperature scale. So we'll use degrees Celsius in our thermometers in the lab. Americans will use degrees Fahrenheit in all of their calculations, and we do see that sometimes as well. But in the gas laws, we're very, very specific about the type of temperature that we have to use, and we measure temperature using kelvins. Oh, that's not very helpful at all now, is it? Let's just see if we can undo that. Switch that over to a highlighter for you. Kelvin temperature scale. Now, Kelvin is a hypothetical temperature scale. It's based on the idea that if we cool off a substance, the particles vibrate slower. If we cool it off even more, the particles will vibrate even slower still. So theoretically, if I get them cold enough, all motion should stop. That point where all motion in an atom stops, all motion is halted, is called the Kelvin temperature scale. We set that baseline at 0 kelvins, and that's what we define as absolute zero. Absolute zero is that temperature at which all motion stops. Now, we have measured this, and we have found out that all motion stops at minus 273 degrees Celsius. So 0 kelvins is the same as saying minus 273 degrees Celsius. Now, again, you're going to notice as we're talking that I'm saying degrees Celsius or degrees Fahrenheit, but I just say K for kelvins. I don't say degrees Kelvin. It's not a huge deal, but that's not a mistake. That's just sort of the way we do it. The really nice thing about changing between Celsius and kelvins is 1 degree Celsius is exactly the same size as 1 Kelvin. So we have it a lot easier than our American neighbors down south of us because they have a much more complicated formula to use in their science labs when they're measuring the temperature of gases. We have to change them from Celsius to kelvins. All we have to do is plus and minus. So this formula here, x kelvins minus 273, gives us our value in Celsius. If, for example, I was doing a problem and we figured out the temperature was operating at 345 kelvins, and you're like, oh, that doesn't make a lot of sense to me. How can I change that to Celsius? All you would do is minus 273. 345 kelvins minus 273 would be 72 degrees Celsius. Now, that's something that has some meaning to us. That would be like the temperature of a nice warm bathtub. Quite often, though, we have to do this in the opposite direction. We could be studying a gas that we've measured with our thermometer in the lab and we've cooled it down to minus 39 degrees Celsius. Well, to change that to kelvins, we have to add 273 degrees. Whatever our temperature is in Celsius plus 273 gives us our temperature in kelvins. Minus 39 Celsius plus 273 is 234 kelvins. Now, it's important for this entire unit that anytime you see a temperature in Celsius, you immediately cross it out and change it to kelvins. If we leave it in Celsius, none of your formulas will work. So that's going to be our first thing that we're going to be practicing. The next thing we need to do is to talk about pressure. And there's unfortunately not just 2, but 3 standard units for pressure. We've talked about this gentleman before. His name is Evangelista Torricelli, and he was that guy who created the idea of standard air pressure in his tests when he was trying to create a vacuum. Now, when Torricelli tried to create the vacuum, and he took his little apparatus with his tube of mercury inside of the dish of mercury and tried to figure out how big of a vacuum space he could be, he found out that On an average day at sea level, no matter where you are on the world, the air could support a column of mercury 760 millimeters tall. He called that standard pressure. Okay? Later on, 760 millimeters of mercury was called torrs after its discoverer. That was called 760 torrs. We now have two other units that are both accepted by the metric system as well, though, the atmosphere and the kilopascal. These three units comprise something that is true. It is a truth. They are all equal to each other. 760 millimeters of mercury is the same as saying 1 atmosphere is the same as saying 101.3 kilopascals. And unfortunately for you, all three units are going to be used, and you might have to do conversions from one unit to the other because we can't mix and match units in a question. So I'm going to show you how to do this using something called unit factor label method or dimensional analysis. Now, I'm going to put up another video in a minute on how to do that. So if you're not understanding, this would be a good time to pause this video and go and watch the other one on unit factor label method. All right, so here's a couple of examples where we would be using the unit factor label method that I talked about in the other video on how to convert from kilopascals to millimeters of mercury, or from millimeters of mercury to atmospheres. Remember, the 4 steps in the unit factor label method are: start with what you know, put the values you're trying to get rid of on the bottom, put the values you want on top, and then step 4 that's not listed here is we multiply across the top and divide across the bottom. So let's take a look at this. In these two questions, start with what you know. Well, in any problem in the sciences, look for the number and its accompanying unit. It tells you a lot about the problem. What I know is that I have 340 millimeters of mercury. That is where I'm starting. I'm starting right there with 340 millimeters of mercury. That is what I know. Then I draw the big long line all the way across, okay, that I have here, and I cut it off. I put the units I'm trying to get rid of on the bottom. So right now I'm trying to get rid of the units, millimeters of mercury, so I write those units on the bottom. I put the units I want, here's the question, the units I want on top. Now, which numbers make it true? Remember, a truth is anything that's equal to each other. We know from the previous page that 101.3 kilopascals is the same thing as saying 760 millimeters of mercury. They're equal to each other. So this is a case of special one. These numbers are equivalent to each other. So what numbers make this true? Well, 101.3 kilopascals is the same as 760 millimeters mercury. Remember, I always start with my units first, and then I find the numbers to make it true. What I'm noticing now is that millimeters of mercury on the top cancels millimeters of mercury on the bottom, and I'm left with the units kilopascals. So I have the units I want. Let's follow the math. Multiply across the top, divide the numbers on the bottom. The order you do it in doesn't matter. I can go 340 times 101.3 divided by 760. I can say 340 divided by 760 times 101.3. It doesn't really matter. The order is irrelevant. We're going to get to 45.3, and the only units we have left are kilopascals. Okay? You're going to notice on some of the videos that I'm going to recommend you watch, instead of writing a vertical line, they'll use a time sign. Again, that's absolutely fine. It's just another way of doing it. I find the vertical line to be neater, especially for my messy writing, but it means the exact same thing. Let's try another example here. How many millimeters of mercury are there in 7.2 atmospheres? Again, what do I know? Well, I know 7.2 atmospheres. Start with what you know. Draw the line and cut it off. I'm trying to get rid of the units atmospheres, so I put the units atmospheres at the bottom. I want the units millimeters of mercury, so I put the units millimeters of mercury up at the top. The truth is, from our formula on the last page, that 1 atmosphere is exactly the same thing as saying 760 millimeters of mercury. These are all standard pressure again. So beside the units atmospheres, I put the number 1. Beside the units millimeters of mercury, I put the number 760. Again, multiply across the top, divide across the bottom. 7.2 times 760 divided by 1, atmospheres cancels, is 5.5 times 10 to the power of 3 millimeters of mercury. Now, I've rounded this off here for significant digits. Don't panic too much about significant digits right now. Those will take care of themselves at a later point. Right now, if you're getting 5.5 times 10 to the 3, or 5,500 in and abouts, you've probably set your answer up correctly, and that's the bigger picture for me. So what I'm hoping you've learned from this video is, can you convert between units of temperature? Can you go from Celsius to Kelvins and Kelvins to degrees Celsius? Can you convert between units of pressure using the unit factor label method? Can you remember and define standard temperature as being minus 273 degrees Celsius, or 0 kelvins? And can you define standard pressure as 1 atmosphere, 760 millimeters of mercury, or 101.3 kilopascals? What I want you guys to work on to help you learn this, we have a worksheet called Temperature and Pressure Conversions in your workbook. It should be almost immediately following this page. If you're needing more help with that, I need you guys to go and watch my other video on how to do unit factor label method. I will be giving you guys about 2 days to get through this lesson, and look for your next post coming up shortly.